the last type of interest point we will study are the blobs, the blob detection. So a blob is an area of an image where some properties are roughly constant and they differ strongly from their surrounding, so a distinct area in an image. Similar to corners, it is different than its neighborhood in all directions. So if I actually move a patch around the blob in any direction, I will get a high change. Its definition, however, is less formal. So some property meaning that, similar gray levels in an area, similar colors in an area, or even similar gradient magnitude in an area. So if I actually look at this image, for example, this eye can be a blob, the entire spectacle can be a blob, this entire arm can also be a blob. So it's less well defined, but that's okay, because we will actually use methodologies that leverages this ambiguity. For blob detection, mostly we will use Laplacian of Gaussian filter, and that's we've already seen. It was the second order derivatives after smoothing the image with a Gaussian. And we see that actually we can do it with the Mexican hat. So if I actually apply the Mexican hat on this image, the response I get is something like this. And notice that the blobs here are actually highlighted as high intensity. So that's nice. Now, actually, I would not use the blob detection in this form directly. What I would do is I would actually use its dependence on the smoothing amount. So the more I smooth the image, basically I will create larger homogeneous intensity areas in the image. So if I now look at the Laplacian of those, I will detect different blobs. So in theory, I can actually apply the Mexican hat filter with different amount of pre-smoothing. So use Gaussian filter with different standard deviations, and then apply the Laplacian filter. And smaller smoothing will basically allow me to detect smaller blobs, like given here, well-defined structures. Increasing the amount of smoothing, increasing the sigma, I see that the result of the blob detection changes. Now, for example, in this case, the eye is a very clear blob, while at the very, very smooth level, I see that the arm here is another blob. Basically, the different scale of blobs are detected. And all these blobs, all these high intensity areas, form actually as interest points. And I know I leave it a bit vague here, because later on, with a very specific example, we'll see how these are used. That concludes our strategy's first part, so identifying the points of interest. In the second part, we'll talk about how do we extract local features from these points of interest. So extracting descriptors around interest points. To recap, a feature should capture something discriminative about a well-localizable patch. So we covered the well-localizable patch idea. And we've seen that actually from these images, we extracted many, many corners or blobs coming out of our detectors. But they still cannot be told apart. What we need now is we need to describe their surrounding patch in a way that we can discriminate between them. So we need to build a feature vector for each patch around an interest point, a so-called descriptor. And during matching or recognition, these descriptors will basically be compared across images or across a database of descriptors. Just to remind, the number of detections can be high. If I look at these images, I see that there are many, many corners that are detected from them. So what I need now is I want a descriptor to really describe each of these interest points. Okay, and remember, I basically will extract many of these points, and these areas are the patches that I want. So actually, in order to create a descriptor, I really need two different components. First, around each point of interest, I should be able to define an area, a local patch in the image. And second, within that patch, I should extract features that represents that patch, either looking at its intensity values or looking at its color values. So I should create a vector of numbers describing that patch. I actually have some additional requirements of the descriptors that I didn't really have on the points of interest. First, I want to be able to detect the same objects or similar categories under different variations of geometric and photometric changes. So, if possible, I want to be able to extract local patches and descriptors that are invariant to such changes. And if invariance is impossible, then these features should be insensitive to such changes. Now, to ensure that this happens, I will actually look at small local patches larger than large, because small local patches can consider to be planar. So their deformations with geometric changes are more stable. I also would like to extract intensity-based descriptors that do not really change with illumination changes. Otherwise, I wouldn't be able to create descriptors around the patch or within a patch that can be matched with different images. Now, the invariance theory for extracting features that are really invariant to geometric and photometric changes is rich and is quite fun. Unfortunately, we don't have the time to get in it, but if you are interested, please contact us and we'll be happy to point you to the right direction. Instead, we will see two different examples of how these ideas are used in practice. First one is called Euclidean invariant features. That was proposed in 1997, so it's quite an old idea, but it was quite useful. The idea is you take an image and you apply Harris corner detector to identify corners as interest points. Then you extract circular patches around each interest point. And for each interest point, you would extract circle areas of multiple radii, so that you can actually account for scale changes to some degree. Then, from the circular patches, you extract invariant features that do not change under planar rotation from an area to another to form the final descriptors. And it has been a very successful model. Mathematically, the features that you extract are the rotation invariant gradient magnitudes. So gx and gy here represent the horizontal and vertical derivatives. And remember, the patch you extract is circular. So you would actually extract the gradients, but you would weight the gradient values using a Gaussian profile centered at the patch center. So this is what they call the Gaussian derivative. That basically gives you an idea that the contribution of a pixel that is at the outer boundary of a patch is less than the contribution of a pixel that's at the center of a patch, close to the interest point. Well, just like the gradient magnitude, you can actually also think about rotation invariant second-order derivatives. For example, sum of the second-order derivatives similar to a Laplacian operator, where gxx and gyy now represent the second-order Gaussian derivatives obtained in a similar way through weighting. Now let's talk about the invariance properties a little bit. First of all, the areas are obviously rotational invariant because they're circular. Second, taking circles with multiple radii at each point achieves some levels of robustness to scale changes. So if I zoom into an image, hoping that maybe I will actually extract a larger circle, I will capture similar information. Now, the gradient magnitude is rotational invariant. That's quite nice. Can you actually show that it's rotational invariant? Likewise, the second-order derivative is also locational invariant, and maybe you can actually try to show it as well. So one question is, while the features that you extract are rotation invariant, and the areas that you extract are rotation and to some extent scale invariant, are these features, the gradient magnitude and the second-order derivatives, are they invariant to scale changes as well? I will leave that question to you. The second example we will see is called SIFT. So it's a very famous feature extraction. It's called Scale Invariant Feature Transform. It's developed by David Lowe, and it's a carefully crafted interest point detection and descriptor based on intensity gradients. And this method is actually invariant, or let's say insensitive, to similarity transformations, or transformations on translation, rotation, and scale changes. Now, the idea is using blob detection. Interest points and patches around interest points are jointly determined by using blob detection at multiple scales. Multiple scales meaning I take an image and I smooth the image with different amounts and apply the Laplacian of Gaussian filter. At different scales, I will get different filter responses, and I will record the extremal points. So this, for example, the 3 images will give me 3 maps of extremal points. And these basically will give me a list of interest points and the standard deviation at which that interest point was a maximal. So this list is quite nice because through this list, I'm able to actually identify the interest points as well as the patch around the interest point. Specifically in this list, X and Y tells me where that interest point is, and the sigma tells me the size of the circular patch I should extract around that interest point. So for example, here, at this point, the interest point, it's actually determined to be a blob after a lot of Gaussian smoothing, so the patch is large. While around the eye, as we've seen before, it turned out to be an interest point after very little smoothing, so the patch around is small. And notice that this, to some extent, captures scale changes. The second part, I have to extract features within those circular patches. So the same patch can be rotated in any direction. And the previous method that we've seen was looking at the gradient magnitude. Now, the gradient magnitude was really rotationally invariant, but maybe it actually loses some information. In SIFT, another strategy is devised. To gain invariance of such rotations, SIFT actually implements what's called a dominant orientation selection to reorient patches so that every time I extract the same patch, despite the rotation of the image, I can reorient it to the same canonical orientation. So given a patch, I compute the image gradients, and I build an orientation histogram for the gradients. I find the maximum. That maximum in the histogram corresponds to the dominant orientation of the patch. I take the image and I simply rotate the image such that the maximum orientation is now facing in the vertical direction. This way, I'm gaining robustness to the rotation changes or possible rotations in the images. To create the actual features, I compute the image gradients sampled over a grid. So I divide this patch into a grid like this, and I compute the gradients at every pixel. Then SIFT actually creates or further divides this entire patch into a 4x4 grid points. So it looks something like this. Here we show it 2x2, but it does it in 4x4. And in each of these grids, it actually computes the histogram of gradient orientations. And the histogram it represents with 8 bins. So really, I look at this patch here, right? It has multiple gradient values. I compute the number of gradients looking at north. I compute the number of gradients looking at south, and so on. And I create these histograms per block. So I have 4x4 block, that's 16 blocks. And each of these blocks, I create a histogram of 8 bins, meaning for the entire patch, I create a representation that's 128 dimensions. Then I apply a weighting with a Gaussian located at the patch center, such that the contribution of the pixels closer to the interest points are larger than the contributions that are at the outer boundaries. And then I normalize it to a unit vector to compare across images. Now, this sounds almost like a food recipe, but actually SIFT is a very carefully crafted. For example, we can ask, why do they actually extract 4x4 blocks within each patch and use orientation histograms with 8 bins? If I actually look at the orientation histograms and look at the size of the descriptor, width of the descriptor, okay? So with 16 orientations, with 8 orientations, or with 4 orientation histograms, and I also vary the width of the blocks. So 4x4 blocks here, 3x3 blocks, 2x2 blocks, and 1x1, so basically 1 pixel. What I show here is the correct nearest descriptor. So I basically extract descriptors from an image, 2 images that correspond to each other, and I test whether these descriptors can be used to match truly corresponding locations in the 2 images. What we notice is actually the correct nearest descriptors, the percentage increase rapidly as I increase the width or the number of blocks I use per patch, and then saturates if I use roughly 4x4 blocks. And after 5x5 blocks, I get the same accuracy. Moreover, if I look at the number of orientations I use in the histogram, if I increase the number, I start getting a big boost in the number of correct matches. But after some point, after 8 orientations, I also see a saturation. Sift or David Lowe looks at these plots and basically identifies this point, specifically using 4x4 blocks with 8 orientation histograms, to be a trade-off between good accuracy and computational complexity. So it can be implemented very fast while being accurate. The interesting thing about SIFT is, so it's designed to be invariant to similarity transformations, but it ends up being invariant to affine transformations to some extent as well. In the experiment here, we basically take an image and simply change its viewpoint. So really create an affine transformation in a sense. And then we look at whether the SIFT descriptors are able to match corresponding locations between images. And it is indeed the case that even at viewpoints, differences of 20 degrees, SIFT achieves quite good detection accuracies, the correctly matching accuracies. Obviously, if the viewpoint is increased higher, so I really create a lot of variation in the viewpoint of a scene, then the correctly matched percentage decreases. But up to 20 degrees, it looks like SIFT is actually quite robust to changes in the viewpoint differences. So briefly talking about the invariance properties. The local patches are rotationally invariant because they're circular, and it's scale invariance due to this dominant orientation selection. It's scale invariance due to patch selection in multiple scales. Now, the rotation invariance actually is enforced in the feature extraction through dominant direction selection. Now, here, as opposed to the previous example, David Lowe uses gradient orientation histograms. And notice that these are invariant to scale changes. The gradient orientation doesn't really change with changing scales. Now, SIFT was a big success, and it has been used quite often in computer vision applications. It's obviously not the final endpoint, and there has been huge improvements over SIFT in computation efficiency, accuracy, and robustness for different transformations, notably by speeded up robust features, surf features, that we will not cover, but I strongly suggest you to look at it for further information. And this covers the two parts in our strategy for identifying points of interest and extracting local features around them to create descriptors per image. And remember, we get many points of interest and extract features from all of them. So we have many features per image, and we hope that these represent different parts of many objects. And in a future lecture that's coming up in 2 weeks, we will see how all these descriptors can be used in real object recognition systems.